Next up is question 4. It says for each function, compute p0, p1, and p2 based at the specified point. Then use these polynomials to approximate the functions at certain values and compute the absolute error in each approximation. And so for part A, we're looking at f of x, which is the natural log of 1 plus 3x. And here our base point A is 0. And so to construct the Taylor polynomials up to p2, I want f of 0, f prime of 0, and f double prime of 0. Okay, so f of 0, that's the natural log of 1, and that's equal to 0. Now for f prime of x, since we're differentiating a natural log, I'm going to get 1 over 1 plus 3x, and then from the chain rule, I'll pick up this factor of 3. So that implies that f prime of 0 is 3. F double prime of x, well, if I just differentiate this expression, I'm going to get a negative 9. I pick up another factor of 3 from the chain rule, and then we're dividing that by quantity 1 plus 3x squared. Okay, so that implies that f double prime of 0 is negative 9. Okay, now recall, this is the expression for the general nth Taylor polynomial. And so for p1 of x, that's where we just go up to this linear term. For p2 of x, that's where we go up to this quadratic term. And I haven't mentioned it up to this point, but p0 of x is just this constant f of a. And the reason why I haven't mentioned it up until now is because, frankly, it's not a terribly interesting approximator, okay? So, in any event, let's go ahead and compute these for this example. So p0 of x, that's just f of 0, and that's 0. For p1 of x, well, that's f of 0, which is 0, plus f prime of 0, which is 3, times x minus 0. And so that simplifies to 3x. And then for p2 of x, well, we have f of 0, which is 0, plus f prime of 0, which is 3, times x minus 0. And then we have plus f double prime of 0, so that's minus 9, over 2 factorial times x minus 0 squared. And that simplifies to 3x minus 9 halves x squared. All right, so now real quick, let's go ahead and take a look at these. So here in blue is the graph of f of x, which is our natural log function. And we're looking at things at this point, 0 comma f of 0, which is just at the origin now. Now p0 of x, which is just equal to 0, right? This is the constant function that passes through this point 0 comma f of 0. Or put it another way, it's just the horizontal line that passes through that point. And again, right, I haven't mentioned it yet because, well, it's just not a terribly good approximator. Okay, now p1 of x, that's our tangent line approximation. That's doing a much better job, as we can see here. And then p2 of x, that's our quadratic approximation, and it's doing an even better job. All right, cool. So now let's go ahead and look at approximating the value natural log of 1.15. And so first I want to just mention, right, that if I want to find the natural log of 1.15, I first have to ask what value of x do I plug in to get the natural log of 1.15. Okay, so do this off to the side. If the natural log of 1 plus 3x is to equal the natural log of 1.15, I need 1 plus 3x to equal 1.15. And so I can just solve for x by subtracting 1 and dividing by 3, and I find that x is 0.05. So in other words, the natural log of 1.15 is really f of 0.05. Okay, so that's then approximately p0 of 0.05, and since p0 is a constant function, right, this approximation is just simply 0. Okay, now for our p1 approximation, plugging in, we get 0.15 for our approximation. And then for p2, plugging in 0.05 gives us the approximation 0.13875. All right, so now if we look at the absolute error, well, for this first approximation, the error is 0.13976. Looking at the P1 approximation, Okay, we're doing a little better, right? The error there is 0.0102, so on and so forth. And then for the P2 approximation, we're doing even better, right? The error there is about 0.00101 and so on. Okay, and so P2 is definitely doing the best job, and again, that is in line with what we're seeing visually here in the graph. All right, cool. So now let's go ahead and check out part B. Make some space there. All right, so here we're looking at f of x, which is the square root of 1 plus 3x, and now we're basing things at a equal 1. And so, just like we did in part A, we'll start out by looking at f of 1, f prime of 1, and f double prime of 1. Okay, so f of 1, that's just the square root of 4, which is equal to 2. Now f prime of x, we're differentiating the square root, so we'll get 1 over 2 times that square root. And then from the chain rule factor, we get this 3 there. So that implies that f prime of 1 is 3/4. F double prime of x, well, if I differentiate this expression for f prime, I get negative 9 over 4 times 1 plus 3x to the 3/2 power. And so that implies that f double prime of 1 is negative 9/32. Okay, so then I'm going to use those values to construct our Taylor polynomials. P0 of x, that's just f of 1, which is 2. P1 of x, well, that's f of 1, which is 2, plus f prime of 1, which is 3/4, times x minus 1. And then for P2 of x, we have f of 1, which is 2, plus f prime of 1, which is 3/4, times x minus 1. And then we have plus f double prime of 1, so that's minus 9/32. And then we divide that by 2 factorial, and then that's multiplying x minus 1 squared. And we can simplify that to 2 plus 3/4 times x minus 1 minus 9/64 times x minus 1 squared. All right, so let's go to the graph, get a feel for what this looks like. So here is our square root function in blue. We're looking at things now at the point 1 comma f of 1. And so there's our P0, right? This is just the horizontal line that passes through this point. P1 of x, that's our tangent line approximation. And then P2 of x, that's our quadratic approximation. All right, so now let's go ahead and use these polynomials to approximate this number's square root of 4.15. Okay, now, again, just like we did in part A, what value of x do I need to plug in to get the value, the square root of 4.15? Well, if the root of 1 plus 3x is to equal the root of 4.15, this is saying I need 1 plus 3x to equal 4.15. So we just set those equal to each other and solve for x, and we get that x here is 1.05. Okay, so this square root of 4.15 is really f of 1.05. So that's approximately P0 of 1.05, which is equal to 2. Now if I plug in 1.05 into P1, I get 2.0375 for the approximation. And then if I plug in 1.05 into P2, I get 2.0371484,375. All right, so now looking at the absolute error there, for our first approximation, we get about 0.037 and so on. For the P1 approximation, we're doing a little better, 0.00034 and so on. And then for the P2 approximation, we're doing a heck of a lot better. It's 0. And then 0.00000, that's 5 zeros, 644 and so on. Okay, so again, P2 is doing the best job out of these three. All right, well, that's going to do it for this question. Thanks.